Our next speaker is Joost Nuiten, and he's going to tell us about moduli problems for operadic algebras.
Thanks a lot, and so thanks for to the organizers for the invitation and also for staying up so late, maybe. So I want to talk about a joint project with Damien Calac and Ricardo Campos, which is about deformation theory in the setting of operats. And a bit more precisely, we work over a field of characteristic 0. This I will do throughout my talk. And as we saw, I think also in Dan Peterson's talk, over a field of characteristic 0, there's this classical principle in deformation theory that tells you that, well, first of all, if you start with a differential graded Lie algebra, you can build a deformation problem out of it. And in some sense, all deformation problems arise from the algebras in this way. And the basic question that we were trying to address is the following. So suppose that you start with a Lie algebra and it has some further algebraic structure. So for example, it could be that the Lie bracket actually arises from just a product by taking the commutator. And then you can wonder, how do you see this additional algebraic structure in terms of the corresponding deformation problem? So what I want to do is I want to start by recalling a bit the classical theory of deformations over commutative algebras. This was also done in Dan's talk already, but I guess I will give a slightly different perspective. And in particular, there will be no operats in this part, but then at some point operats will pop up, and then I will address the question. Okay, so let me start by discussing a very classical example of this principle in deformation theory, namely the study of deforming complex algebraic varieties. So if you start with a proper and smooth variety over C, you can try to study its infinitesimal deformations, which means you start with X, which is a variety over C, and you study families of varieties which sit over the spectrum of an Artinian local C algebra, such that the special fiber is X itself. So these are infinitesimal families of varieties deforming X. And so this has been studied, I guess, in the 50s by Kodaira and Spencer, and they observed that these infinitesimal deformations are essentially controlled just by the tangent bundle of X, and in particular by its cohomology groups. So for example, if you take the 0th cohomology group of the tangent bundle, that's just the module of holomorphic, or say algebraic vector fields on X. And of course, vector fields on X, those are just first order automorphisms of X. So things get a bit more interesting if you go to the higher cohomology groups. For example, the first cohomology group of the tangent bundle classifies deformations of X. Well, it classifies first order deformations of X, so deformations over this ring C epsilon modulo epsilon squared. And the construction, I guess, goes by the name of Kodaira-Spencer map. And then there's also some higher cohomology groups, for example, the second one. And the basic observation of Kodaira and Spencer is that the second cohomology group controls the obstructions to extending deformations to larger rings. So for example, if you start with an n minus first order deformation of your variety X, you can wonder if there exists an n, let's see, I have to do the counting correctly, if there is an nth order deformation that extends it. And it turns out that if you start with an n minus first order deformation, there's some canonical class in H2 of X with coefficients in the tangent bundle called the obstruction class. And this class is 0 if and only if there exists such an extension. So, well, one way to compute these cohomology groups of the tangent bundle is to use the Dolbeault complex. So that's given by essentially by some sort of differential forms with coefficients in the holomorphic tangent bundle. And this Dolbeault complex has some additional algebraic structure, namely it has a Lie bracket, which is built from the commutator bracket on vector fields and the multiplication of differential forms, anti-holomorphic differential forms. And the essential idea is that this differential graded Lie algebra controls all deformations of our original variety essentially by taking Maurer-Cartan elements in a clever way. So for example, if you take, or maybe more precisely, if you take an Artinian algebra A with maximal ideal MA, then deformations of your variety over A are given by elements in this tensor product of the maximal ideal with the Dolbeault complex that satisfy the Maurer-Cartan equation. And in addition, automorphisms of such deformations are controlled by essentially by the action of, well, a certain group, so called the gauge action, on this set of Maurer-Cartan elements. And so yeah, this action you build somehow out of the degree 0 elements of this DGLA by integrating the adjoint representation. So in this way, so you see that the Maurer-Cartan equation is an equation that happens in degree 2 in this DGLA. And that's basically the reason why obstructions to extending deformations sit in the second cohomology group, because this equation also lives in degree 2. And in fact, it turns out that this entire obstruction theory that Kodaira and Spencer set up, it kind of follows from the fact that you can write your deformation problem in terms of differential graded Lie algebras in this way. So all these obstruction classes, they somehow can be cooked up from the Lie bracket. For example, the obstruction of extending a first order deformation to a second order deformation is just given by the self bracket of your class that sits in H1 that classifies this first order deformation. So this somehow tells us that deformations are controlled by the degree 0, 1, and 2 part of our DGLA, but of course there's further terms in this complex, and you can wonder how to interpret those. And the essential idea is that those control derived deformations of your complex variety, which are deformations not over just Artin algebras, but differential graded Artin algebras, which live in, say, negative cohomological degree, such that if you tensor them with your DGLA and you take Maurer-Cartan elements, you start picking up terms that come from higher degree in the Dolbeault complex. Yeah, so just to recall the definition of an Artinian differential graded algebra, so we say that an augmented algebra, commutative algebra, is Artin if, well, first of all, its cohomology is finite dimensional, so there's only finitely many groups and each of them is finite dimensional. The groups are concentrated in non-positive degrees, and furthermore, the 0th cohomology group is just an Artin algebra in the usual sense. So it's finite dimensional and the kernel is a nilpotent algebra. So somehow the higher cohomology groups of this Dolbeault complex control deformations along these Artin differential graded Artin algebras. And now in general, if you start with any differential graded Lie algebra, there's also negative cohomology groups. And these negative cohomology groups typically control homotopies between automorphisms of deformations. And in this case, because we're talking about deformations of a variety, there's no homotopies between automorphisms of varieties. So you don't actually see anything happening in the negative direction. But in general, there could be also homotopies. So yeah, so one can now try to axiomatize this whole structure a bit, and that's done by what goes under the name of formal moduli problems. So this is kind of Grothendieck-like way of axiomatizing deformation problems. So we will say that a formal moduli problem, it's a functor that goes from this category of differential graded Artin algebras to the category of spaces. And yeah, to be precise, by category, I mean infinity category here. So in particular, on the side of differential graded algebras, all quasi-isomorphisms are always inverted. And this functor has to satisfy two conditions. First of all, if you evaluate it just on the field itself, you get the point, which essentially asserts that if you deform something that sits over the point, there's only one way to do it, namely you just take the object itself. And then there's a second condition, which is usually called the Schlesinger condition, which says that certain pullbacks of Artinian algebras are mapped to pullbacks of spaces. And I guess an informal way of thinking about this is as some sort of sheaf condition where we glue the spectra of these Artinian rings except that we don't really glue them along open inclusions, but along closed inclusions. So if you define a deformation problem to be a formal moduli problem, so to be a functor of this form, then this principle that asserts that every deformation problem is controlled by a Lie algebra can be made a theorem, and that's what Pridham and Lurie did. So they proved that there is an equivalence of infinity categories between the category of these formal moduli problems and the infinity category of differential graded Lie algebras, where again, this is at the level of infinity categories, so we always identify quasi-isomorphic Lie algebras. And in particular, if you want, you can also model this category of the infinity category of Lie algebras in terms of L-infinity algebras, which is something that people also encounter in deformation theory. Okay, so let's look at some examples of this theorem, which are of a bit more algebraic nature. I know this is supposed to be a talk on operats, so more algebraic things are better. So for example, one can look at deformations of a module. So let me fix some associative algebra and the left module over it. And I guess I've already been doing that, and I will probably do it even more. I will become increasingly vague about whether things have differentials on them or not. I guess for this, in this example, let's say that there is no differential graded structure here. If there is a differential graded structure, there are some conditions that you have to put on this module for this to actually work. In any case, so if you have a module over an associative algebra, you can look at deformations of it and you can organize them into a formal moduli problem. So what you do is you start with an Artinian algebra and you associate to it basically as the category of modules over A tensor B, such that if you induce from A back to K, you arrive at the original module V. So informally, you think about this as the category of A tensor B modules, such that if you tensor them up, there is a specific equivalence to V. And now in principle, this fiber product, this is a fiber product of infinity categories. So to make this thing work, you have to take derived categories everywhere. And in principle, this fiber product could be an infinity category, but it turns out to be an infinity groupoid, so a space. And now you can check that this particular deformation problem is given by the derived self-maps of V, of bilinear self-maps of V, together with the commutator bracket. So one way of explicitly writing this down is you take some resolution of V, and then you take the actual bilinear endomorphisms of V, which form a chain complex, and it comes with the commutator bracket. And there's also another way of explicitly writing down this complex using the bar construction, which is something that maybe we find elegant if we like operats. So you can use the bar construction to present the derived self-maps of V to V bilinearly. And in that case, the commutator bracket can be written in terms of trees in this kind of form. So you basically start with a map that, well, two maps that take inputs from B and one input from V, and you compose them in the only way in which it makes sense, and then you take the difference with the only way to compose them in the other way. So that gives this complex a structure of a differential graded Lie algebra. So that's how to deform modules. And you can also start deforming algebras. Again, this we also saw in Dan's talk, I think. So if you start with an associative algebra over your field K, you can write down a very similar looking formal moduli problem. And basically what it does is it takes an Artinian algebra and you take the fiber product of the category of algebras in the category of A modules. You take those algebras in the category of A modules such that if you tensor them up to K, you get back your original B. So that's what's written here. And again, it turns out that this is a fiber product of categories, and the resulting fiber product is actually a groupoid. And then this deformation problem is classified by, I think Dan called it the deformation complex of the associative algebra B, and he also said that that agrees with the Hochschild complex. So that's this complex of linear maps from tensor powers of B to B itself. And well, so we know that that thing has indeed a Lie bracket, which is given by the Gersten-Haber bracket, which is the bracket where you take two operations from a tensor power of B to B, and you compose them in all ways you can, and you sum over it, and you take this, well, you add a certain sign to it, and then you do it the other way around. And in this case, the differential of this complex can actually be written in terms of the Lie bracket by just taking the commutator with the multiplication on B itself. I think we also saw this in Dan's talk. Okay, so those are two more algebraic deformation problems. And now the sort of question I want to ask is, okay, so those are all deformation problems that are classified by Lie algebras. But now suppose that I have a map from the Lie operad to some other operad P, and my Lie algebra structure actually arises from a P algebra structure. Then what can I say about the corresponding formal moduli problem? So what's the sort of additional structure that this formal moduli problem has? So let me give you 3 examples. So here's this 0th example, which is a bit of a silly one. So the Lie operad is an augmented operad. So there's the augmentation to the unit operad, whose algebras are just modules. And in particular, restriction along this map just sends a module to the trivial Lie algebra. And now you can wonder, so what does it mean for the formal moduli problem of a Lie algebra to actually be classified by a trivial Lie algebra? And well, if you think about the Maurer-Cartan equation for a Lie algebra where the bracket is 0, you basically see that you don't really use any of the commutative algebra structure to write down this Maurer-Cartan equation. And it basically means that the formal moduli problem is defined just on vector spaces. It only depends on the underlying vector space. So that's a proposition. It's true. If your Lie algebra arises as a trivial Lie algebra, then the corresponding formal moduli problem actually arises from, well, a sort of linear formal moduli problem, which means it's a functor that goes from the category of perfect complexes, so finite complexes of finite dimensional vector spaces in non-positive degrees, to spaces which satisfies a sort of analogous Schlesinger condition. So certain pullbacks go to pullbacks of spaces, which in this case is equivalent to this functor being reduced excisive, which means that 0 goes to 0 and push-out squares go to pullback squares. And yeah, maybe here's one sort of nitpicky thing. So since we're doing everything in infinity categories and not in usual categories, saying that a Lie algebra is a trivial Lie algebra is actually data. So you have to specify a specific equivalence between G and a trivial Lie algebra. And the data of this equivalence is essentially the same as the data of a homotopy in this commuting triangle. So it's data of making the triangle commute. So a slightly more fancy way of saying this is that, well, there's a commuting square where in the bottom there's this equivalence between Lie algebras and formal moduli problems by Pridham and Lurie. And there's also an equivalence between modules and linear formal moduli problems. So these kind of reduced excisive functors that appear here on the right. And this diagram commutes. So it means that, well, a Lie algebra arises as a trivial Lie algebra if and only if the formal moduli problem arises as the restriction of a linear formal moduli problem by just evaluating on the underlying chain complex of an Artinian algebra. So this is a bit of a silly example. Let's do a slightly more interesting one. So if we look again at this deformation problem describing the deformations of a module, well, in this case, the Lie algebra given by the derived endomorphisms of V, of course, the Lie bracket is the commutator bracket. So it comes from an associative algebra structure given just by composition of maps. So actually this Lie algebra is an associative algebra, and on the side of deformation problems, you see something very similar. Namely, if you look at the formula for the deformation functor, So recall that this said that this just sent an algebra A to the category of A tensor B modules, such that if you tensor them up to K, you get back V. Well, this actually doesn't really require A to be commutative in any sense. You can also evaluate this on associative Artin algebras, which are not necessarily commutative. So there's kind of two ways in which associative algebras appear here. On one side, this Lie algebra that we found turns out to be an associative algebra, and we can also evaluate our formal moduli problem on associative algebras. And it turns out that these two appearances are very closely related, because there's also a commuting square, where again, in the bottom, there's the equivalence of Pridham and Lurie between Lie algebras and commutative formal moduli problems. And now there's a variant of this equivalence, which relates associative algebras and formal moduli problems indexed by associative Artinian algebras. And this diagram again commutes in the sense that if you start with an associative algebra and you take only the underlying Lie algebra, the corresponding formal moduli problem is just obtained by restriction. So you just take a commutative algebra, forget that it's commutative, and then evaluate. So I guess this square was already known. This also appears in Lurie's paper. And now, well, here's another example related to deforming associative algebras. So actually, you can cook up two examples here. I only want to do one of the two, which concerns the situation where you deform a trivial associative algebra where the multiplication is 0. And so in this case, we have, again, this Hochschild complex. And recall that the Hochschild complex had a Lie bracket given by the Gerstenhaber bracket, which was obtained by taking, well, basically composing things in all ways in which it makes sense. And now this operation of, and then doing it, reversing the role of alpha and beta in this. And now if you only look at this operation which alpha assert beta, which composes beta in all of the inputs of alpha, then that itself defines an algebraic structure on this complex. And that's the algebraic structure of a pre-Lie algebra. So it's a binary operation, which is not quite associative, but if you look at the associativity constraints, that's symmetric in the last two variables. And now you can wonder, so, okay, we have this pre-Lie algebra structure. How can we think about this in terms of formal moduli problems? And this is a bit less clear, maybe, at least to me. So to address this, let me start by, yes.
I have a question. Is it, so you're saying this pretty algebra structure only exists if I do the deformation problem for a trivial associative algebra?
Yes.
Okay.
So yes, so the reason is, yeah, it's kind of implicitly written, but I did not say it. So the point is that if you start with the trivial associative algebra, then this differential is 0. And the 0 differential is clearly a derivation for this pre-Lie operation. However, if the multiplication is not trivial, then the differential is not a derivation for this operation.
Okay, thank you.
So yeah, so I did not really say this, but the point is exactly that this is a differential graded pre-Lie algebra. If you don't start with the trivial associative algebra, then the differential and the pre-Lie structure are not compatible. Yeah, and maybe I should say, so this looks like a little bit of a silly thing to maybe be looking at, just to deform trivial algebras. But one should keep in mind that essentially every associative algebra is a deformation of a trivial algebra. You can always somehow multiply the multiplication by some constant lambda and then send lambda to 0. So in some sense, once you understand how to deform trivial algebras, you have a pretty good idea of what the moduli space of associative algebras looks like. And I guess we kind of also saw this principle in Dan's talk somehow. I mean, So yeah, I guess one should not consider this as a sort of very exotic or like far-fetched problem to address. Okay, so to give an interpretation of this kind of pre-Lie algebra structure in terms of deformation problems or formal moduli problems, let me now discuss a bit what formal moduli problems look like in this operatic setting. So let me fix, I guess for the rest of the talk, let me fix an augmented operad, which can be, well, which it's always symmetric and it can also be differential graded. And the cohomology groups are concentrated in non-positive degrees. This is a sort of technical thing that pops up at various places. So then first of all, you can make sense of Artinian algebras over such a thing. Namely, we say that an algebra is Artin if, well, first of all, its cohomology is finite dimensional and it vanishes in positive degrees. And second of all, each cohomology group is a nilpotent module over the zeroth cohomology group. And I guess in this setting, one has to be a little bit careful by what you mean by nilpotent. So here is the precise way to interpret this. Basically, if you pick an operation in the augmentation ideal of P, and you pick a bunch of elements in H0 of A, then there is an operation given by applying mu to A1 up to AN, and then you take as input something in HI. And the result will be in HI because I took mu to be of degree 0. That gives you a whole set of operations, and you ask that there exists some natural number such that if you compose n of them, it can be different, then you get 0. So in particular, if you check what this does for the commutative operad, by which I mean the non-unital one, so the one whose algebras are non-unital commutative algebras, then you see that non-unital Artin algebras are exactly the augmentation ideals of the Artin algebras that we encountered before, which were augmented commutative algebras with a unit. Okay, so now once we have a definition of Artin differential graded algebra, of course you can just mimic the definition of a formal moduli problem. So a P algebraic formal moduli problem is a functor that goes from the infinity category of Artinian P algebras to spaces, and it satisfies, well, first of all, if you evaluate it on the zero algebra, which is the terminal Artin algebra, so it plays the role of the base field K here, if you work in the non-unital setting. Then you just get the point. So this says that over the terminal algebra, there's basically only one deformation. And then there's a version of the Schlesinger condition, which says that a certain pullback of Artin algebras gets sent to a pullback of spaces, homotopy pullback of spaces. And now there's the following thing that we prove in the paper, which is essentially an analog of the theorem by Pridham and Lurie. And it asserts that if you start with a Koszul binary quadratic operad, which has to be in non-positive cohomological degrees, that's kind of the running assumption throughout everything, then you can classify P algebraic formal moduli problems in terms of algebras over its Koszul dual. So there's an equivalence between algebras over the Koszul dual and formal moduli problems indexed by Artinian P algebras. So what are examples of this? So you can open the book of Laudet and Valette and check what are the examples to which this kind of thing applies. So first of all, this applies when P is the commutative operad, in which case the Koszul dual is the Lie operad, and you find back this theorem of Pridham and Lurie. If you use the fact that non-unital Artin algebras are the same as augmented unital Artin algebras. So then, well, if you take P to be the associative operad, its dual is the associative operad. So you find this equivalence that I mentioned before between associative algebras and associative formal moduli problems. And I guess then there's a bunch of other examples, for example, the Poisson operad. So that's a commutative product and a Lie bracket, which is a derivation for this product of a certain degree, which are self-dual up to shifts of degrees. And then there's the Leibniz operad and the Zindel operad. So Leibniz is roughly the non-commutative version of the Lie operad. It's like a not necessarily skew symmetric operation which satisfies the Jacobi identity. So not exactly sure what that's good for, but I kind of became a little bit interested in these operads in the last month. Anyway, and there's a bunch more that you can find in the book. So let me make a couple of remarks about this theorem. First of all, this equivalence between algebras over the causal dual and formal moduli problems, it's natural in the operad P. So if you have a map of these causal operads from P to Q, then there is a map between their causal duals. And basically forgetting, I hope I wrote this correctly. So if you, so there's a map from the causal dual of Q to the causal dual of P. And now if you forget forget the P-Schrieg algebra structure to the Q-Schrieg algebra structure in terms of formal moduli problems, that just means that you restrict along the obvious functor that goes from Artinian Q algebras to Artinian P algebras, which also just forgets algebraic structure. So that's naturality. And my second remark is a bit about the terminology. So let's see if I go back. So I denoted this functor here by MC. And that's not without a reason. So this construction of MC, of the functor MC is kind of closely related to the Mauer-Cartan equation. But the precise relation is a little bit subtle. So let me kind of quickly go over it. So the idea is the following. So you start with an algebra over the causal dual of P, which I will denote by G, because usually in the classical case, this is supposed to be a Lie algebra. And you also pick an Artinian P algebra A. And you want to evaluate the moduli problem classified by G on A. So that's supposed to be a space. So now here's how you do it. There's a bunch of steps. First thing you have to do is, well, you have to pick an equivalent algebra to A, which does not just have finite dimensional homology, but it's actually finite dimensional itself as a complex. And unfortunately, I think you cannot really do that in general if you work with P algebras, but you can do it with P infinity algebras. This we also saw in, yeah, I'm sorry, I keep repeating things that Dan said this morning. But so you replace this thing by an equivalent P infinity algebra, which is actually finite dimensional on the nose. And now you observe that there's a map of operads from the L infinity operad to the Hadamard tensor product of P infinity with P Schrieg. So the data of this map of operads is essentially equivalent to choosing to a choice of twisting morphism from P infinity to the dual of P Schrieg. Sorry, I'm saying it the wrong way around. From the dual of P Schrieg to P infinity. In any case, there is this map of operads, and as a consequence, if you take this P infinity algebra A infinity and you tensor it with G, this becomes an L infinity algebra itself. And now once you have an L infinity algebra, you can take its Mauer-Cartan elements. So those are the, I did not write down the equation, but they are those elements of degree 1 such that D of the element plus 1/2 times the self bracket of X plus 1/6 of the 3-array self bracket of X, etc. Is 0. And yeah, so this is not just an L infinity algebra, it's also a nilpotent one. So this, this formula is going to terminate at some point. Okay, so A infinity tensor with G is an L infinity algebra. And now this space Mauer-Cartan G of A, you can model it by the simplicial set of Mauer-Cartan elements where you take A infinity, you tensor it with G, and then you tensor it with polynomial differential forms on a simplex. So that's the kind of the standard formula to get spaces of deformations in terms of Mauer-Cartan elements. And yeah, so you can prove that this is the formula that works. And actually, even in the commutative case, I'm not sure if this was like entirely known. even though, because the way Lurie and Pridham construct this equivalence, it's slightly different. And it's not entirely obvious from the way they define it that this formula indeed does the trick, but you can check that it also works in the commutative case. Okay, so now let me come back to this original question about this, the pre-Lie structure on the deformation complex of a trivial associative algebra. So yeah, let me recall that if you start with a trivial associative algebra, then its Hofschild complex had this pre-Lie structure given by composing maps in all, like along all possible inputs with a sign. So how to think about that in terms of deformation problems? Well, first of all, it turns out that the pre-Lie operad is also a binary Koszul operad. That's a theorem of Chapoton and Livernet. And the Koszul dual is given by the permutative operad. So here I should probably say what the permutative algebra is. It's a bit of a funny thing. So it's an associative algebra such that if you multiply 3 elements together, this is symmetric in the last 2 elements. So in particular, commutative algebras are permutative, and also if these things have a unit, they are automatically commutative because you can just take A to be the unit in that case. So the interesting stuff really happens if you look at non-unital associative algebras that satisfy this condition. And now the theorem says that, well, this pre-Lie structure on the Hofschild complex, it classifies a certain formal moduli problem indexed by permutative Artinian algebras. So now the question is, what exactly is that formal moduli problem? And this is, yeah, I'm sorry, this is slightly complicated. So the pre-Lie algebra classifies some formal moduli problem, and basically what it does is it takes a permutative algebra A and it sends it to a certain space of deformations of the trivial algebra B along A. And these deformations, what they look like is, well, first of all, you have to pick a right A module, B tilde, such that if you quotient out by A, you get back B. So one should keep in mind that A has no unit here. So B times, so all A multiples of elements in B, that's a strict subset of B. And technically for this thing to make sense, the module has to be flat. So in any case, you look at modules over A, right modules, together with an associative product from B tilde tensor B tilde to B tilde, which lands in the submodule of all A-linear multiples of elements in B. And so in particular, that implies that if you look at this product and you reduce modulo A, you get back 0. So it deforms the trivial product. And now, well, so the left-hand side, so the domain of this multiplication map, that now has 2 commuting right A actions. And well, in principle, B does not have 2 right commuting A actions, but all A linear multiples of elements in B, that does have 2 commuting right multiplications coming from A. And these 2 actions exactly commute by this permutative law, which says that if you multiply elements in A from the right in 2 different ways, these things commute, these things are the same. So it makes sense for this map from B tilde tensor B tilde to B tilde times A to be right A bilinear. Okay, and now technically for this thing to be correct, you should not take an associative product, but you should take an A infinity structure. And yeah, then the formula becomes a bit more complicated, but there's a variant that makes it work. And yeah, you can organize these things in a space, and that's the space that the formal moduli problem associates to A. So it somehow is some space of deformations of the associative algebra B along A. Okay, so this was the example I wanted to discuss. And now let me turn to the proof of the main theorem that we have in our paper. So recall that the theorem roughly says that if you start with a Koszul operad, then there's this functor that goes from algebras over the Koszul dual to formal moduli problems indexed by P algebras. So how does this thing get constructed? Well, if you have your Koszul dual operas, P and P shriek, turns out that there's an adjunction between the categories of P algebras and P shriek algebras, and that adjunction is essentially Koszul duality. So the functor D from P algebras to P shriek algebras, it takes this operatic bar construction, and then you take the linear dual to get an algebra over P shriek. And the functor D prime is essentially the same thing, but you reverse the roles of P and P shriek. And maybe it's good to point out that this is really an adjunction between infinity categories. And well, even though this construction of D makes sense already at the level just of chain complexes, you don't get an adjoint pair in that case. So the adjunction only exists at the level of infinity categories. Okay, so basically this adjunction is the key player in the entire proof. The entire proof consists of analyzing what this adjunction does to, well, nice kinds of algebras. So for example, the way this functor MC is defined is you define the formal moduli problem classified by a P shriek algebra G to just send A to those maps of P shriek algebras that go from the dual of A to G. And this is also how Pridham and Lurie defined their equivalence. And now there's something that you have to check, namely you have to check that this functor indeed satisfies the conditions of being a formal moduli problem. So it satisfies the Schlesinger kind of condition. And for that to be the case, you have to verify that the functor D sends certain kinds of pullbacks of Artinian algebras to pushouts of P shriek algebras. Because once you map out of pushout, you get a pullback of mapping spaces. So that's basically what you have to check to make sure that this functor is even well defined. And then to check that it's an equivalence, what you have to prove is that the functor D is fully faithful on Artinian P algebras. And once you have that, there is somehow machinery from Lurie that allows you to conclude that the functor MC is an equivalence of infinity categories. So yeah, so in the end, really the proof comes down to checking statements about this adjunction, taking Koszul duals, and then invoking some machinery from Lurie. And the analysis of this adjunction involves all the sort of finiteness and Koszul conditions that appear in the theorem. Okay, so let me mention some further generalizations of the theorem. So, well, first of all, we don't actually need so much of Koszul duality in this story. If you just take an arbitrary augmented operad, you can also work with the dual of its bar construction, which is also a perfectly nice operad. And indeed, it's true that algebras over this bar dual operad are in, well, let's say in many cases, they are also equivalent to formal moduli problems indexed by P algebras. But there is a list of technical conditions. So the first condition is that there should be no nullary operations, and there should also not be too many one-ary operations, only the identity. And then there's a sort of a funny condition on the cohomology groups of the bar construction of P. And essentially, these two conditions are exactly the sort of thing that start entering in the analysis of this Koszul duality adjunction, and to prove the assertions I showed on the previous slide. So here's one example of an operad which satisfies these technical conditions and which is not a Koszul quadratic operad. So those all do satisfy these conditions. So the example is the little disks operad. And now you could also assert that this is already treated by the Koszul version of the theorem, because the En operad is formal and then it's equivalent to the Poisson operad. But if you don't want to invoke the formality of little disks operad, there's also a version that does not use that. So yeah, second, There is also a version where there are nullary operations and operations in degree 1, but then these awkward conditions become even more awkward. So I don't want to say too much about it. And the third variant, which is maybe the more interesting one, is there's also a colored version of the theorem and also a relative version. So what you can do is you can replace the base field K by, say, a differential graded algebra over K, or if you are in the colored setting, you can replace it by a DG category over K. So in that case, you look at operats which come not with an augmentation to the field, but with an augmentation to K. Well, like big K. So for example, the colored version of this theorem also applies to the Swiss cheese operat, which is now not formal. The only thing is that I don't think we know, maybe someone knows, but we don't, I think, what the dual of the Swiss cheese operat is. I think that involves somehow knowing what the, well, basically what the dual of the map from the En plus 1 operat to the En operat, what the dual of that map looks like. So we haven't completely figured this out. I mean, you can check what the homology of it is, but yeah, I don't exactly know what the dual of the Swiss cheese operat is precisely. Okay, so here's one application of this relative slash colored version of the theorem. So you can apply this to the operat of operats themselves, which we saw in Lucy's talk just an hour ago. Yeah, and since all of this stuff only works for augmented operats, we should not work with the operat whose algebras are operats with a unit, but for the, well, we should work with the operat whose algebras are operats without a unit. Or equivalently, those are augmented operats. Okay, so there's some colored operat whose colored are labeled by natural numbers, whose algebras are augmented one-colored operats. And now this operat is augmented by, well, basically by the category of finite sets and bijections. But since I work with k-linear operats, I have to k-linearize all mapping sets. So this is just a category whose objects are natural numbers, and then the endomorphisms are the group rings of the symmetric groups. Yeah, so in this case, this operat is augmented, and what the augmentation, so if you restrict along the augmentation map, what you do is you start with a symmetric sequence, and you just consider it as a trivial non-unital operat where all the composition maps are 0. And similarly, restricting from O sigma to K sigma just takes the underlying symmetric sequence. So looking at this operat for non-unital operats in this way is kind of useful because this operat O sigma is Koszul self-dual relative to K sigma in some sense. And this essentially goes back to the thesis of van der Laan, where he proved something very similar for the operat for non-symmetric non-unital operats. And then you kind of have to analyze how this interacts with the symmetry groups. And that was done in a paper of Malte Deling and Bruno Valette. And somehow combining these two things leads to this statement. I'm not sure if they explicitly say it like this, but essentially all the ingredients are in their work. So now once we have this Koszul duality, you can apply the theorem that we proved, or at least the colored version. And what you see is that there's an equivalence between augmented operats now and some sort of operatic formal moduli problems. So those are functors which take as input Artinian augmented operats. And now, yeah, you have to now start wrapping your head around this. So what's an Artinian operat? It basically is a DG operat which is finite dimensional. And there's only finitely many ways in which you can compose things. And at some point you reach 0. So these are nilpotent operats. I don't think we're very used to, or at least I am not, to thinking about such things, but okay. Yeah, so this is what the theorem produces. Not exactly sure what it's good for. but well, I think it's a funny statement anyway. And maybe one way to think about this result is to think of these operatic formal moduli problems as being sort of geometric analogs of conilpotent co-operats. And this, I mean, you can make this a little bit more precise by observing that the category of formal moduli problems, it is generated by Artinian operats. Well, actually, it's generated by the formal duals of these things. And now the dual of an Artinian augmented operat is just a nilpotent co-operat. And now this category of formal moduli problems is generated by such objects under co-limits. So somehow one can think about formal moduli problems, operatic formal moduli problems, as things that you can build out of conilpotent co-operats by co-limits. That's roughly what also happens in conilpotent co-operats. Yeah. Okay, so now, yeah, let me make some more remarks about this theorem. So first of all, this equivalence, you can make it reasonably precise. So if you have some augmented operat P, and you want to understand what the corresponding operatic moduli problem looks like, well, it just takes an operat N, it takes the dual operat in the sense of the bar construction, so it's the linear dual of the bar construction of N, and then you take maps of augmented operats from this dual operat into P. That's essentially what comes out of the construction. And there's a kind of nice way to write this, at least if the operat P classifying your moduli problem is concentrated in arities 2 and greater. So in that case, you can also write the value of the formal moduli problem classified by P on N as the space of maps from the L infinity operat to the Hadamard tensor product of P with N. And yeah, there's also a way to describe this in terms of Maurer-Cartan elements. But yeah, let me not do that. So that's the first remark. And then the second remark concerns the naturality of this construction. So to say a bit more about this, note that there is a functor that takes an augmented operat and builds a pre-Lie algebra out of it. And what this thing does, essentially you start with your operat P, you take the product of all arity components of P and you symmetrize. And then the pre-Lie structure is given by exactly the same sort of formula that I depicted before. So you take operations from the operat P and you stack one on top of the other in all possible ways that you can. So along all possible inputs, and you sum over it. And on the dual side, there's also a functor that starts with a permutative algebra and builds an operat out of it. And essentially what you do is you start with your permutative algebra A, and you just build an operat without a unit that's given by A in every single arity, and all composition maps are just given by the multiplication in A. And now you can check that the permutative structure is exactly what you need in order for this to be an operat. Oops. And now, yeah, because I'm kind of uncomfortable talking about non-unital operats, you maybe want to join a unit to it, but this is not particularly relevant. So, yeah, so on the one hand, operats are related to pre-Lie algebras by this product construction, and on the other hand, permutative algebras are related to operats. And these two things are intertwined by the equivalences that I described above. So the equivalence between augmented operats and operatic moduli problems is related to the equivalence between pre-Lie algebras and permutative formal moduli problems by, on the one side, you do this product construction, on the other side, you restrict along the functor from permutative algebras to operats that I wrote down here. Okay. And well, we already had a pre-Lie algebra structure that we were kind of interested in before. And well, here's a coincidence. This pre-Lie algebra structure actually arises from an operat in the way that I described before. This essentially, you can see it from the formulas that I wrote for the pre-Lie structure that were exactly the same as the ones I wrote for on the previous slide. So the operad that gives rise to this pre-Lie algebra on the Hochschild complex is, well, the convolution operads, viewed as a non-unital operad. So you can once again pose the question, okay, so now there is some convolution operad that is supposed to describe deformations of the trivial algebra, associative algebra. And what's the operatic formal moduli problem that is classified by it? And yeah, again, the answer is a little bit complicated. It requires some sort of awkward definition, which is the following. So if you start with any one-colored operad P, you can look at a very big colored operad whose colors are right modules over P1, which is an associative algebra, and morphisms from R of such guys to another one are given by maps from the R-fold tensor product of them to V0 tensor with PR. And now because PR has R different commuting actions of P1, it makes sense for this thing to be right multilinear with respect to P1. So this is a sort of colored operad that you can build out of a one-colored operad. And yeah, maybe just for emphasis, note that if you start with the unit operad, which is just the identity and no operations otherwise, this operad R modules over K, it's not the monoidal category of K modules, but it's really just the category of K modules. So there's no operations of arity greater than 1. Okay, so you can build this big operad. And now finally, it turns out that this convolution operad classifies the following deformation problem. So the input is some augmented Artinian operad N. And what you do is you map it to the space of lifts of maps from the A infinity operad to this operad of right modules over N, which lift the map from A infinity to right modules over K, which just sends the multiplication to 0 and all other components of the multiplication to 0. So in this sense, this thing indeed classifies certain kinds of deformations of the trivial algebra structure to, well, algebras which are somehow controlled by other kinds of operads. And yeah, let me stop here. Thanks.
All right, feel free to unmute yourself to thank Joost.